All right, let's get going here. Welcome back to our BEG seminar series. Today we have the pleasure to host Ryan Pollyea from Virginia Tech, where I went to graduate school. Ryan is an associate professor in the Department of Geosciences at Virginia Tech and director of the newly established Virginia Tech Carbon Collab, a research innovation hub to accelerate industry decarbonization through industry-university partnership. Ryan also holds affiliate faculty appointments at the Department of Mining and Minerals Engineer and the Virginia Center for Coal and Energy Research. His research program specializes in numerical simulation of non-isothermal multi-phase fluid flow with application to geologic carbon storage and geothermal energy systems. This research spans a wide variety of geologic environments, including sedimentary basins, fold and thrust belts, carbonate platforms, and reactive basalt reservoirs, as well as uncertainty analysis in highly heterogeneous reservoirs. Ryan is a contributing member of the Southeast Regional Carbon Sequestration Partnership. His research receives support from Office of Fossil Energy and Carbon Management, ARPA-E, and Southern States Energy Board. In 2022, spring of 22, Ryan was an invited member of the Geologic Sequestration Panel on US DOE Basic Energy Sciences Roundtable on Foundational Science for Carbon Dioxide Removal, which developed a plan for investment in basic research needs to achieve net zero carbon emission in the energy sector by 2050. He teaches courses in groundwater, hydrology, engineering, geology, and numerical modeling. And this time he's here not just for the barbecue, but also exploring some future collaborations. And today he's going to talk about carbon storage beyond the basin, insight into carbon mineralization from reactive transport simulations. Ryan, take it away.
Yeah, oh, thank you, Andres. And thank you for hosting me. That was quite an introduction. So yeah, I'm Ryan Pollyea. I'm an associate professor in geosciences with the affiliations and things of that nature. So I'm a numerical modeler. I've been doing numerical modeling since I was in graduate school and kind of built kind of a program up around that. And I started in the kind of carbon, CO2 multi-phase modeling space thinking about basalt rocks. And this was, almost 20 years ago. Pete McGrail's paper on the potential for CO2 in large igneous provinces had just come out when I was entering a PhD program. And so there was a little bit of buzz around it. CarbFix was just kind of getting off the ground. But there was a whole lot of doubt. There's a whole lot of, and I think there still is in many ways. But so I've been working on this problem in various contexts for the last 20 years. And it kind of ebbs and flows. Right now we're in a flow. There's a lot of interest in carbon mineralization. But there's been some periods where there hasn't been very much interest, and we just kind of keep doing the work and learning what we can along the way. So I'm going to present today some stuff that some of my graduate students have worked on over the last handful of years. And we work in a lot of environments, but I think that the basalt rocks are just fascinating. And so coming down to kind of sedimentary basin, oil and gas country, I thought it would be fun to talk about some of this kind of stuff rather than some of the other projects that we work on. So that's going to be the talk today. And we have a lot of contributors, people. This is my lab group. Everyone works on all kinds of stuff. We have our students and our science team, and we try to get out in the field. Even though we're modelers, we try to see what real rocks look like from time to time. And so a lot of what we're going to talk about today was work done by Alec Yerzinski here, standing in front of a LiDAR. We have a portfolio of projects, and what the sort of theme of this carbon collab is thinking about expanding the footprint of CCS. So, there are mature projects that are going on in Illinois and other places, and we're starting to think about fold and thrust belts and think about carbonate platforms and of course the mineralization. And is there applications in the mining sector for carbon mineralization? What would that look like, and how could that be commercialized? And what are the business models to build up around that? So that's kind of the kind of point of what we do. But at the end of the day, it comes largely back to carbon storage. So I don't think this audience needs to go through this picture, but I put it up here because we've been looking at this picture for 20 years. And it's, this is sort of, how we explain geologic carbon storage to folks. And then we pair it up with, sort of the classical, sort of kind of conceptual model of the four trapping mechanisms, right? From structural to residual to solubility to mineral trapping. And they have this sort of, schematic kind of timing associated with it. And the thing that when I was in grad school, getting going on this, the thing that I was working on wasn't represented on this picture. And I thought that was kind of like, maybe what I'm working on isn't going to work. So I like to start with this picture because when we pair it up with where those basins are, we look at this, the Benson and Cole map, and this is also one that's been circulated around for almost 20 years. And the dark areas are, where we have sedimentary basins. They're reasonably well characterized for oil and gas exploration, and we have a pretty good sense for where geologic carbon storage may work. And then there's the kind of perspectives, things like carbonate platforms and coastal shelf environments. But then there's the part here that says non-perspective, metamorphic and igneous rock, right? And that's basically like the big stop sign. And so when I was kind of coming up in this, with the science, I was actually building my PhD around this part, thinking to myself, boy, this might be a mess. There might be no future here. So we've been continuing to ask this question: can we get into some of these other geologic terrains, particularly with the basalt rocks? And being up in the Pacific Northwest, basalt was what we have everywhere. And there were laboratory experiments coming out to suggest that carbon mineralization is pretty fast in these iron-rich mafic rocks. The geochemical reactions are relatively straightforward. Oh boy, wrong button. The CO2 dissociates in water, gives us hydrogen and bicarb. The hydrogen acidifies the water, that gives us our carbonic acid, leads to the dissolution of your pyroxenes and your olivines. So now we're going to get our divalent cations released. The divalent cations connect with our bicarbonate, and that leads to our stable carbonate minerals. That also releases hydrogen, so we continue, this kind of feeds the reaction, but this basalt dissolution is always the rate limiting step. And so the idea that started out those years ago was, can we, boy, this isn't quite working the way I thought, can we take our mineral trapping 1,000 to 10,000 years and bring it forward, right? And so that's the kind of the basis for what this research is doing. And that changes the schematic that we've been thinking about for 20 years about the mineral trapping part of the storage mechanisms. And so now we compress our structural solubility residual trapping up into the early time, and the mineral trapping is potentially the more dominant mechanism for CO2 storage if these reactions are as fast as some of the laboratory experiments suggest they would be. So that's kind of the premise for what it looks like. There's been some encouraging results. Just a quick review of some of the projects that are out there. We've got the CarbFix project is sort of the flagship basalt mineralization project. They're capturing CO2 and H2S off of a geothermal plant in Iceland. They're co-injecting the CO2 with water, and they're mixing just below the solubility limit so that aqueous solution is dense, and the CO2 is going to sink down to 400, 800 meters depth, and it's going to proceed with the mineralization reaction. Some of the, whoops, I keep doing that wrong button. Some of the preliminary results, back in the early testing phases, they're just very small injections, but they were showing 95% mineralization in less than 2 years. So that was enough to get the capital into the game, and they started to commercialize this. And CarbFix has now been running for a very long time, over 10 years. They're starting to add direct air capture and some other projects to it. And if you go on their website, they're going to brag about storing 100,000 tons of CO2 since 2014. But when we're sitting, well, here we are in Texas. Normally I tell this story in Virginia. But in Texas, we're not far from Chemical Alley, and we know that 100,000 tons of CO2 is not very much CO2. So how do we get this to megaton scale? And I think that is one of the big kind of questions about, the carbon mineralization ideas. Can they get to megaton scale? It's clear that, at this scale, things are probably working okay, but can it scale up? And so that kind of gets to a short conversation about the Wallula project. In 2013, the DOE, through Pacific Northwest National Lab, supported a test project at the Wallula Pulp and Paper Plant in Tri-Cities, Washington area. This is Richland, Washington area. And they put a hole in the ground, and they injected supercritical. And so if you can get supercritical to stay put in a mafic basalt formation and the mineralization is fast, now you can start thinking about these megaton scales, because we know that if we're going to store megatons storage, CO2 storage, we do need to get supercritical. We're not going to be able to generate enough water to mix CO2 and water in aqueous phase to get that scale of storage. So this project went forward, and the small injection, 1,000 tons, They didn't do any mass balance or any sort of to calculate how much had been stored of what they put in, but the post-injection sidewall cores showed widespread CO2 mineralization, and it was shown that the carbon isotopes from the source matched the carbon isotopes from the anchorite nodules that had been posted. That's shown there on the bottom right. So there's a high degree of confidence that the mineralization was from the CO2 that was put in the ground at the Wallula site. And so this project was really encouraging because they also didn't detect any leakage at the surface. But you know, this analysis all was coming out in 14, 15, and 16, and then the enthusiasm for mineralization and for carbon storage itself changed right exactly at about 2017, and so that hole was shut in, and no further work was done on this particular project. Now, these results have led to the more recent Project Hero, which is the carbon safe that's going on in the basalts, and I think that one's in northern Oregon. I don't know the details yet on Hero, but this is kind of the idea for what this would look like if we were to start to go to megaton scale, where we need to inject supercritical. So if we think about large igneous provinces as a way to do that, we can start to fill in some of the buttons. We can start to fill in some of the holes on the basin map, and we can do it in some important spots, specifically the Columbia River, Yellowstone Plateau, Yellowstone River, Snake River Plain area. Importantly, we've got the Central Atlantic Magmatic Province, so this is where I'm coming out from. We have a lot of industry. We have a lot of stranded, isolated CO2 producers that are producing 500, 600, 700,000 tons of CO2, things like cement plants and acetate plants and things of that nature. If we could find ways to mineralize CO2 in this area, we could actually maybe start to make a dent in some of these kind of isolated CO2 producers. And then sort of the big one is the Deccan traps. And I know some of my collaborators at IIT Bombay, they're working pretty aggressively to try to make sense of will this work in their basalt rock. So one of the challenges we'll talk about is that the Deccan traps are a fair bit older than the Columbia River Plateau, and it shows. And so some of these rocks that have already been altered, they become a little bit less reactive over time. But the storage estimates for some of these regions, these are just kind of, back of the envelope types of storage estimates from some of the papers over the last few years, but they show that there's potentially very good storage if the technology will plan out. So that gets us to some of the science, right? That's the kind of the big background on carbon mineralization. The thing that we've worked on over the years, we had a project for a while looking at the Columbia River Plateau, specifically the basalt rocks that form, let me go backwards a slide, that form the assemblage up here in the Pacific Northwest. So what does this mean? Well, one of the challenges that comes with dealing with basalt rocks is that they're just kind of fundamentally different than most of the rocks that we work with. Everything is fracture controlled. We can have rocks with permeability that's extremely high. These are all field scale permeabilities. I put this on, I kind of stuffed this slide in here, or this big here, and to show that basalts, and this is just from Hanford, can range, the permeability, the field scale permeability can vary 13 orders of magnitude, right, within a single, Grand Ronde formation basalt. It's an enormous, the variability is extremely high. It's all fracture controlled. The porosity, the effective porosity can be on the order of 1%, 2%, 3%. So you don't have the pore space, like the matrix pore space that you would think about in a sandstone. And so all of the storage is in these fracture networks. There's still a lot of uncertainty in the multi-phase fluid properties. The field scale, as I just mentioned, uncertainty is extremely high. And within a single basalt flow itself, you can get very highly variable mineralogy just within. It's not a homogeneous, sort of mineral assemblage. These things can be, chemically quite heterogeneous. So that leads to some uncertainty. And then I like this picture because this gives us sort of a conceptual model of what these things look like, right? These are layered formations of lavas that have kind of spewed out over the land surface and they've cooled. And so you get this kind of pancake layering, and they have different thicknesses, they have different aspect ratios, they have, and all those geometric configurations affect the fracture network, which feed further into the uncertainty of the flow regime. So these are extremely difficult rocks to flow in. And that's been one of the challenges that Hanford has had for years, trying to clean up the radiation out there. So this gets to some of the science that I want to talk about today. We've done a lot of work over the years with kind of field scale injection models and that sort of thing, but I think one of the important gaps and areas that is fun to explore is what's going on sort of at this outcrop scale, at the scale of an individual basalt flow. So I'm going to talk about a study that Alec Gerzinski did for his master's degree in our program, and he was interested in what are the effects of permeability uncertainty when CO2 is leaking up from below. So the conceptual model would be something like this. You're putting CO2 into a basalt formation, and it's going to kind of rise up to this entablature zone. I'll talk about this in a minute, and it'll start entering the kind of fracture networks. And what's going on? What are the kind of fluid dynamics that are going to control what's going on as CO2 migrates up into these entablature fracture networks? And we're going to think about this sort of at the kind of 5-meter scale, right? We have, there's core flood models that people do. There's large scale, site scale models that people do. But I think this is an interesting scale that not a lot of work has been done. So to understand why this conceptual model matters, we have to talk for a minute about what is the basalt flow. What are the characteristics of a basalt flow? Actually, I guess this one's more centered in the room. So when you have one of these lava flows come out on land surface and cool, you get a couple characteristic features. And it's based on the cooling history. So cooling is taking place in 2 regions, at the surface and at the base. At the surface, we have convective heat flow. It's drawing heat off, and we're generating our kind of typical cooling joints, our thermal, mode 1, just kind of vertical joints that you would see in an outcropper. And if you look at them in plan view, it's like the Devil's Walkway or Devil's Causeway in Ireland, where you get the nice polygonal network kind of stones that you're stepping on. Those are the columnar joints. You get the same thing forming from the bottom. These ones tend to be a little bit tighter. And then in the middle, where these cooling fronts meet, so this is a slow-moving thermal front because it's conductive heat transfer out the base, faster cooling front from the top, and when they meet, you get these really kind of, and they're quite beautiful in outcrop, fanning columnar joints. And so this is what we call a basalt flow entablature, and these have been tested in the field, and the permeability tends to be quite low. They're considered sort of a barrier to fluid flow. We think in the presence of a multi-phase system, there might actually be some capillary trapping going on in these sort of fracture networks. So the question that we're asking is, if our permeability is up here in the upper colonnade and the lower colonnade, then 2 flows stacked on top of each other, you'd have a permeable upper colonnade juxtaposed with a permeable lower colonnade. This would be the injection zone. There may be some trapping potential up here in this entablature zone right here. So what we're going to ask the question is we're going to try to figure out, what's going on in these fracture networks as CO2 is coming, is slightly overpressured in the reservoir and it's starting to try to work its way through the fracture network. That's the question that this first study is going to take a look at, and that's kind of the basis for why we think it's important, because this is, if mineralization is going to kind of take on down here, these things need to hold the CO2 long enough for that mineralization to take place. Furthermore, could the mineralization in these types of entablature fractures actually seal the fracture off and lead to a self-sealing system? And so this is where this talk is going to go from a science perspective. So this is the work. This is LiDAR. This is ALEC in front of the LiDAR. We went out to this outcrop shown on the bottom here. We set up five scanning stations in yellow squares here. We set up the targets for merging the scans, or the blue circles. And we shot this outcrop, merged our scans, something like 150 individual points, extremely small registration error. And what we ended up doing was just focusing. In the end, we thought we had a really nice shot of the entablature section in that blue box there. And so this is the section of the scan that we're going to focus on. We took the LiDAR scan and ran it through a surface roughness algorithm that actually I wrote. So this is an old Fortran program that I wrote when I was a PhD student, but it just takes it calculates the roughness within a grid. And the idea is that if we have kind of a cube and we have an irregular surface in there, like the edge of a fracture, that would be rough. And if it's hitting kind of a flat, smoother surface, that's an unfractured part of the outcrop, that would be smooth. Simply take a binary transform for fracture and matrix. We get this kind of pixelated thing. It doesn't look like much. And then the question is, what does the permeability distribution look like? We found a fracture aperture, caliper measured fracture apertures from Hanford, something like 600 of these things. And we took those measurements with the standard parallel plate correlation to permeability, and we came up with a permeability distribution. And then for the fractured portions, right, so all those black squares, we applied that permeability distribution, and we randomly we drew from that distribution to populate that picture there. And so this is the permeability at these little 2.5 centimeter pixels. Each get a permeability from the distribution, and it looks like this down there. And so, because we don't know what the real permeability distribution would be, we generated 50 of these equally probable, spatially random draws for the permeability distribution. So we're going to simulate that CO2 leakage into all 50 of these, and then look at the ensemble statistics to see if we can learn anything interesting. The model domain is relatively straightforward. We're assuming that the CO2 is going to have about 0.5 megapascal of head behind it, and it's going to be kind of pushing up into the fracture network. We set this up. This was Alex's thing. He was really interested in what happens, you know, can we even model CO2 phase change? It becomes kind of a challenge iteratively if you're flashing back and forth between supercritical and subcritical CO2 on the Newton-Raphson iterations. It's kind of a tough challenge. It's kind of a tough problem. He wanted to try it. And so we set the critical threshold here. So this is our fluid pressure. We're just right at the critical point, 32 degrees C. So as CO2 comes in, right, it's going to cross over the critical threshold, and it's going to flash to gas, and then we're going to have a gas phase. So that was Alex's kind of thing he was interested in. And so this is the model domain. We're going to overpressure at the bottom with CO2, pure water to start. And this is what 2 of our realizations look like after 1, 5, and 10 years. You can see that these are just different permeability distributions, same scenario. Things kind of are relatively similar, and we got to see where the gas and system goes from gas phase to supercritical phase, and that's fully dependent on permeability for these models. The individual simulations don't tell us very much. They're interesting, but they don't tell us very much. But when we take a look at the ensemble average, so now we're going to take the mean CO2 saturation and the standard deviation for all 50 models across the entire, for each pixel, right, for each little 2.5 centimeter square. Now we start to see some interesting things. This is, again, 1 year, 5 year, 10 years, mean CO2 on the top, standard deviation on the bottom. And what we're seeing is that, on average, we tend to see these higher CO2 saturation portions show up when the CO2 has to make a choice. It's coming up a kind of a main fracture trunk, and then it can go off into, you know, it can find some new path. Here it's going to the right, straight up, to the left. And when there is a choice to be made, the CO2 tends to accumulate at these fracture intersections. We thought that was kind of interesting. We also noticed that when that happens, the standard deviation is low. So that means that this CO2 tends to accumulate in all of our realizations, independent of permeability. And so what we kind of came up with this idea is that we think oops, I went too fast. We think this is just a relative permeability effect. Once that first path is established, the gas phase saturation goes up. That means the permeability available to that phase goes up, and that allows more CO2 in, and that's a self-reinforcing path. Okay, and so depending on the upstream permeability in this fracture, that's going to choose. But at the end of the day, we always seem to be getting some accumulation of CO2 at these intersections. And we didn't think much at the time. We thought it was an interesting result. But we think that that's probably going to be important for the reactive part of this when we start talking about reactive transport simulations. So we also took a look at the phase partitioning, and of course the permeability affects the phase partitioning because it affects the pressure as the CO2 is moving through. So that was less interesting. The 2 things that we really focused on for these results is that we do see CO2 accumulating at fracture intersections, which is something that the Vado zone community has seen in the work with regards to the Yucca Mountain stuff. When they're doing a lot of unsaturated flow studies, they saw, you know, if you had a kind of a complicated fracture network, flow would tend to converge onto a single path, you know, as you're starting to fill up, water starts to infiltrate an unsaturated fracture network. And then the fracture network accumulation. So this led to the next study I want to talk about is, will these things seal themselves when you take into account mineralization? So that's the natural extension for Alex's work, and this is what Wu Hao picked up for the final chapter of her dissertation several years back. She basically took the same idea. She went into Rick's model and said, I want to think about what's going on where CO2 has to come up and make a choice. And so she put together a very simple model, right? We have a main trunk fracture, It's going to branch off, there's a couple fractures, and her thought was if CO2 is accumulating here, the flow rates in each of the branches are going to go down, there's going to increase the fluid residence time, and this is where you may get some aqueous phase trapped and you may focus mineralization ahead of the fracture branch beyond these intersections. And if that were true, then what would happen was that the CO2 flow would start to pinch off and this little fracture system could potentially seal itself. So Wu Hao wanted to test that numerically. And she put together a very simple model, 2.5, same general scale as Alex, 2.5 meter by 2.5 meters. She put a little 5 centimeter, this is where the fracture is going to be, just a kind of a grid cell approach. Overpressure of the base by 50 kilopascals. Similar initial conditions, although this is all supercritical, there's no subcritical here. Mean fracture permeability, basalt matrix permeability is going to be very small, very low using tough react. We used the relative permeability model from Sally Benson's group. Marital Grant was a postdoc with her back in the late teens, and they did some micro PET scans to show, to image the CO2 in the basalt. That was actually kind of a challenging little study, but what they found was that there's really only one mobile phase at a time in these basalt fractures, and we thought that was very interesting. So we implemented that relative permeability model. For the geochemical system, Don Rimstead and I worked on this problem up at the top here. This is some experiments that Gudbranson did, and this is Icelandic basalt. So he did some whole rock basalt dissolution experiments where he normalized the rock mineralogy to silica and then ran the experiments, looking at the silica release rate, and came up with this is the stoichiometry for the dissolution. So he published all this data, but never fit a curve to it. So Don Rimstead, before he passed, we worked together, and Don did some of the leverage plots, and I worked on the, kind of fitting it into the Pollyea and Caraca model. But we came up with a dissolution model for crystalline basalt, Icelandic basalt, that is both pH dependent and temperature dependent. And we put it into a formulation that we could get into the tough react code. So that's what Wu Hao used for this study. This is the basalt that she's simulating geochemically. We're going to use the kinetic constraints from the dissolution model that Don and I put together. That's this one here. So we're going to dissolve under kinetic constraints. We're going to allow calcite, magnesite, siderite, and a couple of clays and some silica to precipitate. And we're just going to turn this Y-shaped fracture loose and see what we get. We did add one wrinkle, and Wu Hao is very interested in permeability and permeability change. There's not a whole lot of data yet to really help us inform what some of the correlations look like for permeability porosity in these fracture networks. We know that in a parallel plate system, we can use the porosity permeability relationship where this exponent is a 3. That's a standard parallel plate permeability alteration model. But then if you go back to Verma and Prusa's works, they allow this exponent to be free, and and it's going to increase the strength of the porosity permeability coupling. So smaller changes in porosity will get us larger changes in larger reductions in permeability. So thought that we could use something like this to just sort of schematically consider, as your exponent increases, you could be talking about nodules forming in a fracture, small change in porosity with a larger change in permeability as this kind of pore throat gets smaller, all the way up to a complete bridge, where you bridge a fracture and the almost infinitesimally small change in porosity, you could just completely shut the fracture off. And so we ran this model through that Y-shaped fracture for 0, 3, 6, 9, and 15. We did all 5 of these exponents N on this permeability porosity coupling just to see what we would learn about the effects on fluid flow, and what would that mean if we could actually get some empirical data to support how is permeability changing in these basalt fractures, because we know it's not 0. We're pretty sure it's not a parallel plate. There's something else going on that we just don't know, and we haven't found any experiments to kind of explain what that might look like. So the results of Wu Hao's study, how am I doing on time? We're doing good. The results of Wu Hao's study are, they're interesting. So the way this is organized is we have n equals 0, that's no permeability alteration. N equals 3 is parallel plate permeability alteration. And then 6, 9, and 15. Okay, so that's how this is organized. And then these are the alteration products in this fracture This is our CO2 saturation, and then we have mineral mole fraction for calcite and clay, and then we have mineral volume fraction for calcite and clay. And as we would expect, the calcite, has a relatively high mole percent with very small volume percent, whereas the montmorillonite, when it does precipitate, has a much higher volume percent. So this is just because the molar volume of montmorillonite is higher than the molar volume of clay. And so this is kind of what what the alteration products look like, at least kind of spatially for our different models. We looked at the permeability change with time in the fracture, and so introducing some new language, we're going to talk about the intersection and the middle branch. So we recorded permeability change right here at the intersection and up here in the middle of one of our branches. And we're looking at log K over time, right? So for n equals 0, that would just be a straight line across. There's no permeability change. For n equals 3, we get a little bit, right? A couple, about an order of magnitude over the 10 years, all the way up to, many orders of magnitude, pretty much shutting down the system. So we did see sort of a characteristic crossover. The permeability is fastest here early, where CO2 is coming in sooner. But then as CO2 gets out to that middle branch, the permeability change kind of crosses over and becomes more aggressive down gradient. So we learned that. The important part of this whole thing, I think, is coming up in the next couple of slides. We look at the Darcy flux of CO2 through these fractures as permeability is changing over time. If we have no alteration, if we're not accounting for mineralization in the fracture, the Darcy flux initially goes down, relative permeability effect. As the saturation increases, the permeability available to CO2 goes up, and we see our Darcy flux monotonically increasing over time. If we have any amount of permeability alteration, our Darcy flux goes down, and it's related to how fast that permeability is shrinking, right? So this all makes sense. And we see that both in the middle branch and in the trunk. So this started to tell us something about the usefulness of our non-reactive models, and that they might not be telling a very good story. And then when we looked at the mass balance for this system, we took a look at, of all the CO2 that went in the system, how much of it is in mineral phase, and we compared that to how much went in, right? So what's the ratio of mineralized carbon? I think we did this on a mole basis, right? The mineralized carbon to total carbon in the system. If we have no permeability alteration, we mineralize about 57% of the carbon that goes in. If we have any amount of permeability alteration, we're mineralizing north of 80%. And if we go back to that CarbFix slide, we remember that they were showing in their work, in their early works, when they were doing the radiocarbon tracers to figure out how much CO2 were they mineralizing, they were mineralizing on the order of 95%. And that was for a subcritical CO2 injection. This is supercritical leakage into an entablature fracture network, and we're seeing north of 80% mineralized in 10 years under that sort of 50 kilopascal, kind of a leakage signal type of driving potential. So that's what we came up with for this study. And that gets us to our insights. We have Alex's non-reactive study to kind of parlaying that into Wuhao's reactive study. We think that the CO2 will converge on discrete flow paths. We see that the CO2 likes to accumulate at fracture intersections. We think that's a relative permeability effect, and that the reactive transport models with no permeability alteration are going to substantially underestimate what carbon mineralization will actually do in situ. And there is potential for self-sealing. We saw that with some of those Darcy curves, that the Darcy flux, it was going pretty close to 0 over time. But in a 2D model with not a whole lot of empirical data behind it, there's still a lot of uncertainty there, right? I think that there's room to. I think that this type of work can kind of help us. Like if we learn this thing, we can make better. We can actually be able to say this is real or potentially real. Where right now this is sort of proof of concept. We can see it, and it would be really great to to be able to get some laboratory data behind it to really make that case. So. We think that there's some insights here to be gained. We're certainly not making any broad conclusions that carbon mineralization is going to save the atmosphere and the world from impending doom. But I think that there's a role here, whether it's small-scale generators, whether it's mafic mine tailing. That's an area that we're exploring at Virginia Tech. We have a project to inventory the mafic mine waste in the Mid-Atlantic. Can we use that, fill reaction vessels with this stuff, mineralize carbon in it, and then turn around and use it for road base, like in some sort of a circular economy type of approach? Are there ways, other utilization mechanisms that can make, that can benefit from mineralization? I think that I think the answer is going to be yes. I think we're a long way from that, but I do think that studies like this are kind of helping kind of guide us and give us a little bit of hope that, yeah, this is the technology that has legs. So that's all I have for you today. I guess I'm a little on the short side, but plenty of times to answer questions and dodge stones and that sort of thing. Thank you.
Thank you, Ryan. Yes, we have plenty of time for questions. We start with the room, and then we can monitor what's happening online as well.
You guys can arm wrestle for it. Peter, go ahead. Sue.
Please hold the microphone close.
Well, I have 6 or 8 questions. So,
Okay.
one of them is basalts have been altered over geologic time.
Yeah.
So who's doing work on what we can get out of analog? I remember a really interesting discussion decades ago by Professor Subarao walking on the Deccan and talking about zeolites and talking about. He thought that you could use zeolites to map stratigraphy, and he found out that no, they were wet cross formational, cross flow units.
Yeah.
And I thought that was bad news, but I haven't had anybody back to it to say how does alteration occur in basalts?
Yeah.
And what does that tell us? Anything we need to know?
So we know alteration occurs in basalts. I'm much more familiar with the Columbia River basalts. One of the things that we see in the more recent stuff, in the younger stuff, is that there's kind of a glassy mesostasis that surrounds some of the crystals, and when that is intact, it's much more reactive because the glass phases, the solubility constants on that are quite a bit faster than the crystalline. But when you get into the deeper, older basalts that have been exposed to more water, particularly in the plateau, where you have, they have USDW down to 3-4 kilometers depth. There's extraordinarily good water out there. That mesostasis has been eroded or has been altered already, right? And so they become less reactive over time.
So these zones that are more less permeable with the curve.
Yeah, the entablatures. Yeah.
The entablatures. How does the diagenesis of this compare to the zones that are more permeable?
Well, when the cores that I've seen don't have a lot of alteration in them. I mean, it's not like there's hydrothermal fluid circulating through the rocks that we're seeing in places like Hanford. Doesn't say that there isn't some, there are clearly, clays and things that have formed, but it's not as widespread. They're pretty clean fractures, and I think it's because they're getting exposed to a lot of meteoric water that's, pretty thirsty, and it'll, carry, it'll dissolve and carry stuff with it, right? So there's just not a lot of dissolved solids down there to be, kind of precipitating and causing, that diagenetic type of behavior that we think about in the clastics.
Solution enhancement fractures.
Yeah. I think. Yeah, and those entablature fractures are very tight. When we look at them at the surface, and when we do, Berkeley Lab did some pump tests in entablature fractures, sort of in an outcrop where they kind of drilled, 20, 30 meters back from the outcrop, and this was the Snake River Plain. They were very low permeability, and then as soon as you get under that entablature zone, the permeability comes up again. So the idea there is, it's not speaking so much to what the mineralization looks like in situ, but that those tight fractures they're pretty tight, and they're potentially short-term seal to allow the mineralization to take place. Now in the Columbia Plateau and places like Hanford, we have pump test data from entablature zones in some of these layers that are 10 to the minus 16, 17, 18, and it's extremely low. Whether they're just tight or mineralized, I don't know the answer to, but I think they're just tight.
Well, fractures are annoying because you have to hit the one that's causing the trouble. So I wonder if we could get more out of analogs.
Well, the thing to remember about these, I close on this picture on purpose because these things are so fractured that this is one of the few crystalline rocks where I feel like I could actually make a reasonable argument that the equivalent porous media approximation is a reasonable approximation. I mean, these vertical joints are, they're a foot across, and you look at them in plan view, and you have this nice polygonal network. I mean, these things they're going to be strongly anisotropic, but they are extremely fractured, and so it's not so much of the it's not like the discrete fracture that short circuits, your geothermal system or something. These things are so dang fractured that, if you can get into one of these kind of big zones, there's a lot of permeability there and potentially a lot of pore space even in those fractures themselves.
In the second last slide, I think you made a very short but very essential comment. It's 2D, right? What you have.
Yes, that's right.
In 3D, obviously, I would assume the CO2 is actually fingering within a fracture, right? Mm-hmm. So it goes in and out of your plane of the model, right?
Yep.
So if you seal the fracture in one spot, the CO2 would actually go behind around. So
yeah,
I think what I would encourage you is obviously the hard part, then go to the 3D.
Yeah. Well,
simulation, right, and look at how that works.
It's almost like a 2.5D topology. It's a really weird topology, and we've thought about this where you have a just basically take one of those, in tough it's a finite volume kind of approach, right? And so we could make the whole 2D thing itself the fracture, throw the permeability distributions on it, to allow, kind of to try to emulate like the asperity contacts and things of that nature. And what's going to happen in that topology? I think we will definitely see fingering, but I also think that these sorts of numbers I think this is going to hold up, because we're seeing that. It may not pinch it off completely to zero like we saw in Wu Hao's model, but I think that it's going to get pretty low, because as you start to force that CO2 around, you're also forcing the CO2 saturated brine brine or water in front of it. And that's where you're getting the mineralization front. That's the reaction front. It's ahead of the supercritical CO2.
But you overestimate or underestimate the time it takes to seal off the system, right?
Yeah, the time will absolutely change, correct.
And significantly, actually, right? Because to seal it on one spot is much faster than sealing out in the third dimension the entire fraction. And that's what we see.
I'm not going to disagree wholeheartedly, but I am going to push back a little bit, because you're talking, if we're talking about, you already have the asperity contacts on there, so that now you have sort of like a perforated kind of, like a, Plinko board, right, from Price is Right. Do you guys remember Plinko? Yeah, right. So the CO2 has to kind of take the circuitous path through that plane of the fracture, and it's only going to take you pinch off, one of those with a little mineralization, you force it another long way, eventually you're going to pinch out of there. I think it's going to be different, but I don't think it's going to be off either. There's still something there. We just have to figure out what it is.
I wasted a good amount of my time looking at this crystal geyser thing in Utah, right?
Yeah.
Which is much larger as a fault scale, right?
Mm-hmm.
But it's the same issue. It's the CO2, which is coming out groundwater system, comes up along discrete points, map you along the fault. Yep. And we know from the dating of those deposits that it's kind of jumping around. Right?
Yeah,
so it's actually the same thing, right? It's, if you look at the fault as one of those fractures, right? It moves around.
Over what time scale?
I don't know, thousands, 10,000s of years.
We take that,
so
right? We'd be very happy with thousands of years.
They're a big system too, right? So, but it does the same thing, the same physics, right? So it goes the easiest path.
Sure.
And as you incrementally seal it off, then it always finds it.
But you're always making it harder, right?
It makes it harder, but well, I don't know actually, with that multi-phase flow,
I know.
It may actually, the resistance may not
you're right.
change
It could be a crock. I'm not, but I think the science here is worth chasing. This is, because first of all, it's a lot of fun, but there's a story and it could work, right?
And you could do a model actually in 2D, just looking at the fracture.
Yeah, that's right. And I think that's where we're probably going to end up going next, is let's look at just the fracture plane, and maybe we can, get a little bit fancier just a 2D wide. Agree completely. Yeah. Although it did take that model like 6 hours to run. These reactive models take forever.
Any other questions? Yes.
Give him the mic.
And hold the microphone very close, like you might hear, like American Idol.
Like I'm on The Price is Right?
You like that Plinko? That was a good one, huh?
The model, the boundary condition, that Dirichlet boundary condition, it's gas-based CO2 percolating up?
Yeah. So what both models, the kind of the rock started fully saturated with water. And because we're working the Columbia basalts, we just let it be pure water because that's very high quality, water. One of the reasons why CO2 sequestration out there may never happen is because it's such good water. But we put a Dirichlet condition on the bottom of overpressure with pure CO2, and we just let that pure CO2, under buoyancy, and then the head behind it kind of, propagate through.
Okay, so it's buoyancy, and then it dissolves in the water and
Yeah.
then reacts with the rock.
Yep.
Is there any, have you modeled when that water, then the water gets dense and then kind of fingers down, is that included in there? Or do you see that?
We didn't look for it. I don't think that we would see it here because we have this, we have this overpressure at the bottom. So we have the buoyant CO2, and we're also giving a little push to work its way through. And the permeability of the basalt itself is pretty low. So I don't think we're going to see that, sort of kind of, that dense aqueous phase fall off like we would see in a more homogeneous type of system. What is happening is that the CO2 saturated fluid that's just out in front of the free phase CO2, that's just getting pushed through the fracture into the upper boundary. Okay. Now, we have done some reservoir scale models where we've done CO2 injections into kind of heterogeneous permeability distributions that are reflective of the correlation structure on the plateau. And with those, we absolutely see the CO2 goes out and you get that dense plume of aqueous phase and it's sinking, and the mass balance on those models was about 25 to 30% of the total CO2 mass was just, sinking down under, because it was dissolved in.
Cool, thanks.
Yeah, anyway, long answer to an easy question. Yeah.
Any other question, Mark?
Great talk, I really enjoyed it. Question, and I appreciate, you're doing some modeling, not really thinking about injection per se, but do you have any thoughts on injection rates and also thinking about the Iceland experiments?
Yeah.
Is there any constraints from those experiments that would help you understand if these results are about right?
The constraints on the Iceland experiments aren't really relevant to the supercritical problem. Their constraint is going to be water. It will always be water. They're co-injecting CO2 and water, so that what they are putting in is an aqueous phase CO2. And most places in the U.S. would have a very hard time coming up with the amount of water that you need to do that sort of problem. I've always focused on the supercritical CO2 injections into these basalt rocks, because I think that if this is going to be a meaningful contribution to the sort of climate mitigation challenge, it's got to be a supercritical. It's got to be a megaton scale per site towards sort of operation. And so we've done that. I didn't present it today. One of my other students, he did a whole series of sort of site scale models where in one of them he injected into, we fixed the permeability of the borehole based on the Wooloola site, and then we calculated a spatial correlation model based on the Hanford data and all that permeability data we have. And so we did some spatially correlated sort of permeability fields, and we injected against 95% of the bottom hole pressure of the frac gradient at, I think it was 850 meters depth. And when we did this with a wide range of permeability that exists on the Columbia River Plateau, we got everything from 2.5 megatons over 2.5 million tons over 30 years to like 75 million tons over 30 years. I mean, just the range was enormous, and it all comes down to the permeability, and there's such an enormous range of permeability. And so to, I think, do something at that of a site scale for specifically the Columbia Plateau, we need to do a whole lot of drilling to really try to understand and probably get some kind of improvements in geophysics. I don't know what the state is now, but my understanding from 10 years ago was that seismic in basalts is a real challenge because they're such noisy rocks. So, trying to get a sense on in situ geometry is really hard. Anyhow, so to answer your question, we think that it could be everything from trivial to game changing, right? It depends on what the permeability is going to be, and there's so much range out there. 13 orders of magnitude in one, kind of rock type, is pretty wild. Yeah. Can you drill horizontally in basalt? Okay, that'd be fun. I'm in.
Right, we have a question online. Catherine, you want to ask the question, or should you just read it?
I guess I can read it. Yeah, so I'm asking just overall, what are the main differences between injecting, dissolved CO2 and injecting supercritical CO2, because, the need to co-inject with water, I feel like is a big limiting factor for the technology. And so what just overall is the difference between doing that both in the reactivity and the transport?
So I think on the reactivity side, some of the science is sort of slowly becoming more apparent, but generally speaking, supercritical CO2 is considered to be non-reactive. Now there's some work coming out of PNNL that's showing you can get this kind of thin film of water at the, solid CO2 interface, and that there's some reactivity there. But that's still fundamentally a water-driven problem, so that when you inject the supercritical CO2, you're not actually injecting a reactive fluid. That CO2 is going into formation as a pure phase, and then it's dissolving with the water that's there. Now you have the water, the CO2 in the aqueous phase at the leading edge of the CO2 plume. That's the reaction front. That's where you're going to dissolve the CO2 and potentially drive some reaction out in front. So in terms of what's different, the actual process of mineralization is really kind of the same. It's CO2 dissolving in water, and the dissociation in water, and then you're going to dissolve the rock through the kinetic process, and then you're going to generate the divalent cations and produce the carbonates and clays and that sort of thing. And so the challenge with the supercritical side, and the question that I think is the limiter for it, is will the CO2 stay in the reservoir long enough for the mineralization to actually become meaningful, or is you just going to put it in the basalt pile and it's going to use all these fracture networks and go screaming out the roof? I think that's the limiter for the supercritical side, and the limiter for aqueous, what they're doing at places like Carbfix, is the water. Just simply coming up with enough water to co-inject the CO2 with water into the formation. So that I think does that answer your question or come anywhere near it?
Yeah, that's great. Thanks.
You're welcome.
Sue?
Wait, microphone.
So how much water do you need to drive the mineralization reaction? It's because you need water in order to do the deed.
Yeah.
So what's the I guess we could get out mass balance equations.
Yeah, it depends on the pressure and temperature. It depends on the solubility of CO2 and water.
But I was just wondering about, you have a dry out zone, the water will be gone there.
Yep.
Then you'll have an area that's two-phase, but you got rail perm problems. So the CO2 being more mobile, the water being less mobile. And so how you're gonna? So you need to put. I wonder how much water you got. You want to do this mineralization, so I wonder, how you put the recipe together. How much water do you have to supply?
Yeah.
Driving force. And as you said, this is an important question about about bubbles. About two-phase flow. Yeah. Two-phase flow doesn't happen easily. And it's a special case where you get both together. Usually you get one or the other. So
yeah, I reviewed a paper that was just published recently, so I can talk about it. And it was by she's a former postdoc at Columbia, and she runs a company called Cella now. It's a little climate tech startup for carbon mineralization. They're all over the LinkedIn. But this particular study actually, I think, was trying to get to your question, which is doing a kind of a water alternating gas type approach. Inject the CO2 and then do a water drive. So now you have a reaction front out in front, and then you also have a reaction zone in the back, right? So and and so by doing the WAG cycles, you're kind of sort of trying to kick that mineralization process from both sides, and then driving the CO2 through that. Her argument was that it worked, that the models kind of supported it, but I think it suffers from a lot of the same uncertainties that we talk about here. We just don't know how permeability is going to evolve and that sort of thing. But so to answer your question, my understanding is that at kind of typical injection pressures and kilometer depth, under a 25 degrees C per kilometer type of gradient, so maybe 35, 40 degrees C down there, the solubility of CO2 in water is going to be something like 2 mass percent, CO2. So that's a lot of water. Right.
it should be not too hard, right, to cook them all together and find out a volume of water that needs to be available for to allow the reaction to proceed.
Yeah, I think that we're just assuming there's an infinite supply of water for this.
I think that might be
Right.
a fun place to
Yeah.
fun place to go next to
Yeah, yeah.
understand the need for WAG.
Yeah,
We'll talk tomorrow.
Yeah, yeah.
We think if you've got, once you get the permeability down, you're not doomed.
yeah,
We talk about not the need for a seal. So
Right.
I'll talk to you tomorrow about.
yeah.
I think that a good enough is good enough.
Well,
the
so the-
stacks matter of things. So.
These entablature fractures are so tight in some places that they almost seem like they might set up to be a great capillary trap, right? I mean, if you get a real narrow fracture aperture and you put the capillary barrier across it, that may be enough to slow it down on its own as well.
What I meant was if you put 3 of them together, the potency goes way up.
Yeah, yeah.
That old paper by, I can't remember the name, anyway, Celia and Nordbotten, talking about attenuation
Yeah.
in porous media as you leak. The same thing happens in spades for the confining zone. So I think that you don't have to have a perfect confining zone to be good enough to do the work.
Right.
You just need to stack them.
Yeah,
So because the first one gets most of it, the second one gets everything, nearly everything.
yeah.
and nothing.
Third one never sees it, yeah.
So then you get enough.
Yeah.
Enough to seal them.
I mean, if you go deep enough in something like this, that's
So
that's
I'm
possible.
I'm onto the behavior of water. How
Okay.
it's going to handle the pressure, what the water's going to do, and where you're going to get enough of it, and how it's going to, because the water is so important in the chemistry.
Right.
There's no advection of water in the sort of boundary now.
Advection of water? Yeah, we're driving water. Sure. Yeah, the CO2 is going to displace the water. Yeah, I mean, the water is perfectly mobile in these simulations.
Yeah, but at least that's going to drive up your reaction rate. So I would imagine the, sorry about that. I've never been told my voice wasn't loud enough. Okay. If the water is advecting, it's going to transport the CO2. I'd imagine the reaction rates of the CO2 or the aqueous CO2 with basalt, that's fast.
It's fast, but it is the rate limiting step in the mineralization process. The carbonation tends to be faster. From my understanding is that the rate limiting step. Whoop, I just covered my mic. The rate limiting step in carbon mineralization is always the dissolution of basalt.
Okay.
Because
I guess you've got a two-step problem because you've got to transport the CO2 to get there.
Yeah,
So
and
if the water's not advecting.
and it is going to be sensitive to the dam Kohler number, so that if your flow rates are too fast, you're going to reduce your ability to mineralize as well, right?
Yeah.
And so there's that part of it. You want the stuff to be moving, but you don't want to be moving so fast that you shut down the I guess it's the DA1 gets too big and you lose your ability to mineralize.
Cool.
Yeah.
Neat problem.
Well, I wanted to answer to Sue. So Geographic has calculated all of that, the water demand, and they have some great curves that you can refer to. And so so it's a matter of, it's a function of pressure. So at about 200 meters, your water demand goes way down.
Yeah.
So if you want to inject CO2 dissolving water, then you have to target deeper than 200, 250.
Yeah, it's a solubility. Are you talking about the CO2 dissolution in water? No. Or? It has to happen, but then you have to do all the steps. Right. How much water do you need to do all the steps?
Yeah. And including all the things, including we're going to change outlet. I just got out of my depth. About how much water do you need in a pool? Add 2 cups of water and rock.
Yeah, I bet the ex situ people, the ex situ people, I'm sure have looked at that because that's going to be a limiting factor in ex situ mineralization with these topside reactors that people are starting to build and talk about. Well, but I don't think the water availability is a problem in the subsurface. The problem is the mixing. And if you're mixing topside, you have to pump the salt water from somewhere to make the carbonic acid to put underground. Okay, yeah.
We can produce the water.
Yeah,
right?
yeah.
And maybe I conclude the discussion here, since I'm waiting for the microphone. I think one which we haven't really addressed is, I think the ultimate limit is the reservoir pressure. Because I'm coming from the geomechanics side. You obviously haven't touched this, but the question that Catherine asked, do you want to dissolve the CO2 in the brine in the surface? Or it comes down to how do you maintain a reservoir pressure that you mentioned the frac rate at some point, right? And obviously, if you inject the dissolved brine, it's heavier, so you take advantage of the high density of the water. But that is ultimately rate limiting in terms of how much you can inject, right? Because you have to make sure that you don't exceed locally in the reservoir critical pressure. So I think that needs to be factored into the whole discussion in terms of rates, right? How fast can you inject without exceeding the critical pressure, right? So it's the chemistry that's rate limiting, but it's also the physics that's rate limiting, and then ultimately the economics. How many reservoirs do you need?
Yeah, and
this efficiently, right?
that's why I talk about, the economics is why I talk about the water availability for aqueous injection being the rate limiter, because if you're going to draw that water up from somewhere, you have the energy to do it, and then you have to pipe it, and you have to build a mixer, and you have to get the permits to get that water, and there's going to be a kind of a social problem with that.
There's much more than just the chemistry, right?
Yeah, that's why water, and that's why the water availability is the problem for the carb fix style. They can do it in Iceland because they have more water than they know what to do with, but you couldn't do that in Washington State or Idaho because those waters have been those aquifers have been under stress for the last 60 years.
All right, and as I understand, actually in a lab, definitely the pH of the solution is very important because you're injecting at low pH and the rock buffers it. So you're going from a dissolution to precipitation by changing the pH of your aqueous solution. So, all right, with that, we're going to conclude and stop here. Thanks again, Ryan.
Thank you, everyone.